Welcome back, my lovely students. So you guys already have access to Mrs. Schroyer's videos for these sections. So I'm just going to post a kind of highlight reel of these are the problems people tend to have the most trouble on, or like ones I would typically put on a test. As far as I can tell, these are not on your test. So if you have to choose, go study for your test. These can wait. All right, so I assume you're back and you're done studying for your test and you took your test. Good. So let's see this ugly mess. So this is about the ugliest exponential you can get. And there's the extra letter in there just to trip you up if you're not used to seeing E yet. So let's go ahead and talk about this one. So the whole point is to get at the n. And the n right now is stuck as a power of e. So I want to get that e to the power by itself. So I want to cancel out the 3 and cancel out the 4. The 3 is being added. So the opposite of adding is subtract. So we're going to subtract 3 from both sides of the equation. Minus 3 here, minus 3 here. So now we have the 4e to the 2n minus 5 equals 8 now. And now I don't like that 4 being there. So that's 4 times e to the 2n minus 5. Opposite of multiply is divide. So we divide both sides. Now we have e to the 2n minus 5 equals 2. All right, so we got the e by itself. Now we want to get the exponent to a place where we can solve for it. I use the phrase we need it on the line as opposed to up above the line as an exponent. I believe Mrs. Schroyer says baseline. Either works. So in order to move any exponent down, it's logs that have that property. That is what they were designed to do, is bring exponents to the line so we can solve for them. Most of the time, it doesn't matter what log you use. And even here, you could just do regular log base 10. You just have an extra thing you have to divide over. But whenever you get e, make use of the natural log. It's like the problem is doing you a little favor where you don't have that extra calculation step. So I'm going to take the natural log of both sides. And my LNs can look a little funny. I don't like cursive because then it starts to look weird. So I tend to go with capitals. All right. I really don't like little ln because it looks like one n. And when you look at your notes later, or sometimes even in the middle of a problem, I've had people go from this is a natural log to suddenly this is 1 times n. And then it's n on the next line. And then the whole problem goes, yee. All right, so we took the natural log because it's going to take this whole exponent as a thing and power down to in front of the logs. So that power down is going to become 2n minus 5 in front. And then just for a moment, I'm going to write the natural log of e. And then, of course, over here we have the natural log of 2. So the natural log of e, if this was any other log, then we'd have that as a number there and we'd have to argue with it. But in this case, the natural log of e to what power is e? 1. So that becomes a 1. And then 1 times something is just the something. So that's why a lot of people just cross it off, because it becomes something that doesn't have an impact on the equation anymore. That's why we use natural log. So now our equation is just 2n minus 5 equals whatever ugly number the natural log of 2 is. So just remember, anytime you have log or natural log of a number, it's a number. So sometimes I'll just kind of think of it as put my thumb over the natural log and just be like, all right, 2n minus 5 equals 2. And I'll kind of close one eye so I don't see it. What would I do to solve for the variable? I'd add 5. Okay, I'm going to add 5. Now this 5 does not add to that 2. We're just going to get, I prefer to write it in front of the log as 5 plus the natural log of 2. And the only reason I prefer that is because if I type that, I know the calculator won't screw it up. I am used to extremely old calculators that were stupid, like calculators from the 80s and early 90s. They were very literal creatures. So if you wrote natural log 2 plus 7, sometimes it would do the 2 plus 7 first, thinking like, oh, obviously you meant that. And then it would take the natural log of 7 instead of taking the natural log of 2 and adding 5 to that result. Joys. Then last step, 2 times n, we're going to divide by 2. And we're going to divide this whole thing by 2. So when you're going to crunch this in the calculator, put some parentheses around the 5 plus natural log 2, or crunch that as one step, and then take your answer and divide by 2. Now let's see what we get here. I am oftentimes surprised by the sophistication of the phone's calculator. All right, so here, natural log of 2, because the phone's calculator, I never can tell if you guys can see that there, like puts parentheses on there, just like y'all's fancy calculator does. Old school calculators like didn't used to do this. It would, yeah. All right, so I can close the parenthesis and then add 5. And I'm going to hit equals, and now I have this ugly decimal. Yep. And now I'm going to do divided by 2, and it'll just tack on at the end my thing. But on a TI, it would say ANS divided by 2, meaning whatever was on the previous line is now getting divided by 2, and we get 2.84657, yuck, 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 yuck. So on these equations where the answer is not going to be pretty, sometimes Alex will want this more, what we call the exact answer. And I'm putting quotes around it because that's kind of a misnomer. So here, let me add that over here. So the exact answer, or solution, since this was an equation we solved, is 5 plus the natural log of 2 all over 2. Now, if you forget the curly braces, Alex won't give you any shit for it. Well, okay, it'll tell you you should write them, but it won't take off points. I was trying out one of the problems and I typed 7. It was like, actually, the answer is the solution set 7. I was like, oh, thanks, Alex. But you gave me credit, right? Yeah, okay, good. Yeah, so little on the formal side. So in mathematics, that is the exact answer. The natural log of 2 is not a decimal that stops. It's an irrational number that continues on forever. So when I say the natural log of 2, I mean that precise thing. If I change it out for a decimal, it's only an approximation. But if you're going to do anything with these numbers, if you're going to do any application with logs and exponentials, you don't want the exact answer, you want the approximate answer. So why mathematicians have the obsession with exact answers, I think it's just an aesthetics question, honestly. All right, so when in doubt, I'll go with 4 decimal places, but Alex will for sure tell you. And honestly, if you don't see in a test question how many to round to, then you ask yourself one of 2 questions. Either I was supposed to get a whole number answer or an answer that terminated quickly and I didn't, so I made a mistake, or do I think there should have been rounding directions and the teacher forgot to say? Because that can happen. I've done it every once in a while. That's why I try to double check my tests now. All right. So that is how to solve one of the uglier exponential equations when you only have one exponential expression to deal with. And then we get these. Now, I yoinked this one out of the book because it is by far the ugliest. Because we have 2 bases that cannot be equal, and we have 2 powers that have multiple terms. So this means this problem is going to look really bad, but the steps are not that bad once you get past the first log step. Like they're normal steps you've done, it's just you're having to write a weird thing for a number. So Our variables are in the exponents on both sides. So luckily I can apply a log to both sides. Has to be the same log. So I can't do log 2 on one side and log 7 on the other. Doesn't work that way. You don't do square root on one side and cube root on the other. Has to be the same kind of log. And since it doesn't matter, but we're probably going to have to crunch this answer, go with log or natural log. Since I just did natural log, I'm going to do log. So we are going to apply regular log to both sides of the equation. Now, technically, kind of like square roots, you don't write a square root backwards. Logs technically go on the left. That's how we write them and we apply them. Although I suppose if you saw some European math, they might write it the other way around. Sometimes they do. It's weird. All right, but either way, we're using the logs to power down. So we're going to bring the powers down. Now, since the log of 2 and the log of 7 are not going to go away, make sure those powers come down in safe math parentheses. So here's 1 minus 6x on the line. And this is now times whatever decimal the log of 2 is. And then over here, the 3x plus 4 comes down. And this is times the log of 7, which is some slightly different ugly decimal. All right, so my x's are on the line. I can solve this, and it's linear, so I don't have any weird quadratic. Any of the times you have to do this where log of 2 or log of 7 are staying in, you're not going to do this with a quadratic. It's a disgusting mess. You guys could do it. It's not impossible. It's just ugly. You end up putting log numbers into the quadratic formula. But this one, we just got to get our x's on one side, get our non-x terms on the other side, and then we will have a big ugly fraction at the end to crunch in the calculator. And there's technically some things we can do to make it like look prettier, but really you want the decimal. All right, so if it helps, again, you can kind of put your finger up and ignore the log. If that was 1 minus 6x, whoa, don't touch the screen, times 2, well, then I distribute the 2. So we're going to do the same thing, but it's the log of 2. Some people find it helpful to just go ahead and crunch some decimals now and write them down, and then just work it through seeing the decimals there instead of writing log all the time. And that actually works pretty well, especially for people who seeing it with the logs just does not compute. Feel free. I would just carry a lot of decimals, because if you only carry 3 and the rounding directions are for 3, you could actually end up off by a digit in the last decimal place, which then Alex just will be like, nah, more than likely. It might take it. I mean, they might have some tolerances, we can hope. But here, distribute. And likewise, the log of 7 is also going to distribute. Now, so things don't look confusing, we tend to write the logs after things. That's also because of the way the powers come down, we write them in front. If we wrote them after, it would look kind of confusing, because it would be like, are we doing 2 times 1 minus 6x? Or is that 1 minus 6x times the log of 2? So just to keep up, to hopefully prevent that confusion, I'm actually going to give both of those their own little sets. So everywhere I write it, I'm going to put parentheses around them just to be very clear. It is the log of just 2. So we have the log of just 2 minus 6x times the log of just 2 equals 3x times the log of just 7 plus 4 times just the log of 7. So again, you could just think of them like they were 2 and 7. What would I do if it was just those numbers? And just do that. So I have number minus numbers multiplied to x, more numbers multiplied to x on the other side, and just number. So this should be closer to finding an inverse. Like you guys have a couple of those on the test review, where you end up swapping the x and the y, and then you have to solve. And sometimes you end up with something like this, where you've got x's on both sides. We're going to get all of our x terms, or it might be y terms, sorry. But we're going to get all of our x terms on one side. We're going to get the non-x terms on the other. And then we will factor out and divide by the crud. So which way we move stuff doesn't matter. It's truly a whichever way you want to go. It'll all work out in the end. I generally, though, like this, it's minus 6x log 2. So I don't like minuses if I can help it. So I'm going to add it. Now, normally 3x and 6x would add, but the log 7 and the log 2 being different mean those aren't going to add the way you think they will. So when you're doing these log kind of things, don't combine anything. Just leave everything separate. All you're doing is manipulating and moving. And then at the end, you'll type in a long thing, but you know you haven't put stuff together wrong. So because my x's are now on the right, this 4 times the log of 7 is going to get moved to the left. And again, I don't know how, like obviously they're going to subtract, but those are two different kinds of decimals, so I can't combine those in any nice way. Certainly there's some log properties I can do to actually condense it to log of just one number, but why? The calculator does just fine with multiple logs now. I mean, it's not a bad skill to have, it's just a little out of place historically now. All right, so let's write our end result, well, our intermediate result. So this is the log of 2 minus 4 logs of 7. And then over here, this is, I'm going to switch the order up just a little. So this is x times 3 log 7 plus x times 6 log 2. So I did it that way so you can kind of see when we factor the x out, the 3 log 7 like are still attached by multiplication. It's just the x that's going to come out. And the same over here with the 6 log 2. So when I factor that x out, it is going to be 3 logs of 7. And you can crunch that, plus 6 logs of 2. And you could crunch that. And that is some ugly decimal. And then over here on the left side, I have some ugly different decimal. So I have decimal equals x times other decimal. I want x by itself. So we are going to divide. So that crazy thing is what we're going to be typing in the calculator with more parentheses than you know what to do with. Safe math when it comes to using a calculator. All right. So we're going to divide by ugly mess here. I missed a parenthesis, my apologies. All right. Now for the newer TIs, like if you hit fraction, it actually gives you a fraction and you can fill stuff in on the top and the bottom. But if you have an older calculator or a smaller calculator that doesn't give you a fraction that's top and bottom like this, then what you need is extra parentheses. So the top needs its own set and the bottom needs its own set. So now we would just type from left to right along the top, divided by from left to right along the bottom. So you can do this all in one line of calculation, like just 1 times hitting equal on the calculator. It just looks really crazy. I like writing my parentheses down on the screen so I can kind of check. I see 2 to start with, so I should see 2 here. I gotta change it back to this format, and then I have the log. And my calculator opens another parenthesis there, so I have to close the one around the 2, and then I have to close the one around the log 2, which technically we don't need, but again, I'm used to older calculators where it made a difference. Oh, that's why. And then my calculator is forcing me to write 4 times log 7. So that is all crunched up, divided by. And now we open this one. Now, if you have a calculator that'll let you store things in memory, you can calculate the top, store it in memory, calculate the bottom, store it in a different memory, or just you have the bottom and then you do memory recall divided by answer. And it might work like that. Otherwise, calculate the bottom first, put that in memory, calculate the top, then do divided by memory recall. All right, so 3 times the log of 7 plus 6 times the log of, the log of 2. All right, let's see if we can get that on screen some. You know, I might, yeah. So that is a horrific mess, but that is how it looks on an older style calculator where it won't make a fraction look like a fraction. So if you only get like a linear style calculator, that's what it's going to look like, or one way it could look. Like I said, you can do it in stages as well. But all that, so our ridiculous fraction there, I'm not rewriting it again, I'm lazy. That's the exact answer. But honestly, for a question like this, there's too many ways I can write that. And Alex would not be programmed to handle all of them. So a question like this, all it's really going to ask for is the decimal. So this is negative 0.709289. So 70928. So it comes up to 7093, but negative. Now, kind of zoom back out for a sec, look at our original problem. So with exponentials, I can put negative numbers in there. I can do 2 to the negative 3.5, whatever it would come out to. It's some ugly decimal, but here negatives are allowable. I say that because when we start solving the log equations in a minute, negative numbers I can't take the log of. So once you get to start weird equations, like it's not a bad idea to check the answer and make sure what you got checks out, especially on log equations, because one of them almost always cancels. Sometimes everything cancels and you're left with no solution. All right. I wrote bonus here, but since I didn't see Mrs. Schreier cover it in her video, I'm going to skip it. I wrote bonus because it wasn't in the homework that I saw. So now we have some log equations. So I don't want to completely solve the first one, but I want to talk about the way I would write the first step. So the way I think about these and write these is a little bit different from the way most teachers teach these. And it's not to say the other teachers are wrong. I want to push the concept of what's going on behind the scenes more, because if you guys can grasp onto the concept, it's less rote memorization. Kind of like following the step-by-step maps. Like, sure, you could just pull those steps out every time and just follow them like when the voice tells you to turn left and turn right. But if the voice ever fails, like you're stuck, you don't know where to go or what you could do, or there's construction here, I need a different route. You know, if you got an active phone, sure, it can find you a different route, but if it's just steps, maybe not. But if you understand the route, you understand the different which ways you can get there, then you can still do it even when weird stuff bumps in the road happen. All right, so the way I would write the first step here, so there's a log of one thing equals a log of another. So the book has the equality property of logs or something, where it basically says, if you have the same base on the logs, then the insides are equal, if the logs on the outside are equal. It does have to be one single log and one single log on each side. So later on, we're going to have an equation with multiple logs. You have to condense before you can actually undo that. But for me, the step I would do to solve this is going to be the same step that I would do on ugly mess down here with the ends. This one. I'd condense the logs first, but then what I do is I apply an exponential to both sides. Now it's going to look a little weird, but the idea is when we are solving like the very original exponential equations, if you look in Mrs. Schroyer's notes, if we can write an exponential equation where it's like 2 to the x equals 2 to the y, and x and y can be ugly messes, but if I can write them so they have the same base, then the exponents are the same. They must be equal. So the reverse is also true, with the caveat that you may get some extraneous solutions when you apply an exponential. So just to kind of like round it out, so you see, so if I was going to go back to the exponential here, I would write it as applying, I call it a 2 caret just because that's what you call the little arrow up thing. It's Shift 6 on the keyboard, but it's grammatically called a caret. I would apply the exponential to both sides. Now for this equation, it's not doing anything, but that's what it would look like if I was going to get it back to the line above. That's the kind of thing I'm going to do here. Logs were designed and crafted to undo exponentials. They are the inverses of each other. So we can use them to undo, just like if I had the square root of something, I would square the whole thing to undo the square root. Same idea here, but the thing that undoes log base 10 is 10 as a base with a caret. So that is 10 caret and 10 caret. Now for this to work, it does have to be single log equals single log. So that step still holds true. You still have to condense the logs as much as possible. But now that I have those 10 carets, that is the undoing the log. And we did actually have this in the property section, like there was the whole, 2 to the log base 2 of x is just equal to x. The 2 and the log base 2 cancel out. Or log base 2 of 2 to the x is just x, because log base 2 and the 2 cancel out. They actually become a 1 and the x would go on the line, but you get the idea. So same thing here. So now I just have the equation x squared plus 7x equals 18. With the caveat that, well, we see it's a quadratic, so we're going to get 2 solutions. But the catch is they both may not work. In fact, it is very rare for both of them to work. Not impossible, though, since we have the actual x squared inside the log here. That might be okay. But some of our later ones where the logs are separated out, that's when especially one or both of the answers won't work. So I'm just going to solve this really quick. We minus the 18 over, and we have x squared plus 7x minus 18. So that is going to be x plus 9 and x minus 2. Should still have those equal zeros. So I have negative 9 and positive 2 as my solutions. Now to check those, you literally substitute it back into the equation and see if it would give you the log of a negative number, or what I would call bad math. Like remember when we had the crazy rational equations, we'd take the solutions and plug them back in and see if we would get a divide by 0. It's the same kind of idea here. I'm checking to make sure I don't get bad math. Now we just have an extra thing that equals bad math, or non-real math, perhaps I should say. You don't square root negatives, you don't divide by 0, and now you don't take the log of a negative or 0. because the log has an asymptote there. So we also can't log 0. We can have a log equal 0, but we can't take the log of 0. All right, so -9 in place of x squared. Let me just write it. So that's -9 squared plus 7 times -9. -9 squared is going to be 81. 7 times 9 is only -63. So this is going to be positive. And in fact, it actually does work out to 18, or at least it better, because that's what we had on the other side. So even though it's a negative, when I substitute it into the equation, it doesn't give me bad math. It looks a little weird, but it is technically permissible. If I put the 2 in there, 2 squared plus 7 times 2 is fine. I'll still write it just to be more formal, but and that is also a positive number, and in fact is positive 18. So the big thing I wanted you guys to notice was the way I talk about canceling or undoing logs and what this notation is, what it means. Now, a lot of math teachers do not write this notation. I don't think I've ever seen it in a book, honestly, which really annoys me. But this is how we use inverse operations, the same way that I was adding something to both sides earlier or subtracting something from both sides earlier. Same thing here. All right, I'm going to pause it and put ugly log equation in a separate video, because I'm for sure going to push you guys to watch that one. That is like the #1 test question that all of my students would screw up somewhere, because there were way too many spots where you could make a mistake and yet ponder, why was I putting it on the test then?